Alrighty. Let's go down. Good morning, everybody. Welcome back to non-Euclidean geometry. Plan for today is we're going to talk about one last model of geometry, the Poincare disk, very fancy non-Euclidean model. And then we're going to move into our next packet on quadrilaterals. Usual office hours for the next few days. Today and Wednesday after class and at 2, tomorrow at 11 and at 1. I did post a homework on Canvas over the weekend, homework 5. It will be due Monday a week from now. Homework 5 is consists of questions from the last 2 packets. So the neutral geometry packet as well as the triangle packet. Oh, I forget we might need a little bit of the quadrilateral packet. There's so much. Any questions or comments before we get started for today? Fact quizzes, good job. I will post solutions. Happy to talk about them otherwise. What did the mathematical acorn say on the day that it finally grew up to become a mighty oak? It said, gee, I'm a tree. Gee, I'm a tree. Geometry. It's a pun. Okay, so last time when we left off, we were looking at triangles in several different forms of geometry. We saw that in Euclidean geometry, the angles of a triangle always have to add up to exactly 180 degrees. In spherical geometry, they're going to add up to more than 180 degrees. And in the model U, which was the unit disk, where our lines were just snip off lines as chords on the unit disk, also had 180 degree triangles, despite being a model of hyperbolic geometry. And so, what I want to do today, to start off, is look at the last couple pages of this packet. And we're going to introduce a new model called the Poincare disk. So we've seen the name Poincare before. It's perhaps because Poincare is one of the 7 millennium problems in math. These math problems that if you solve, you get paid $1 million. It turns out that out of those 7 questions, only one of them to date has been solved, and that is the Poincare conjecture. I'm not going to get into what that is now. That's a topic for the last week or so of this semester. But Poincare disk, it's similar to U in that our points are going to be x, y in R2, satisfying x squared plus y squared. Is strictly less than 1, meaning that once again, we're going to be looking at points that are inside of the unit disk. So our points are going to be defined in the same way as they are in the model U that we've been looking at. Lines are going to be defined differently, though. Are anything that's of one of 2 forms. The first type of line is a diameter of the disk. Where a diameter is just a straight line in the sense of how we're thinking of Euclidean straight lines that connect 2 opposite points on the disk. So opposite points on the unit circle. So something that would be a diameter would be, watcha, I just made this circle into a theta. And I connected 2 points that are opposite each other on the circle. So that would be a diameter of the circle. Area of the circle is pi times half the diameter squared in Euclidean geometry. This is not going to be a diameter. Why is that not a diameter? Megan?
They're not opposite points.
Right, they're not opposite points. Similarly to how in spherical geometry, when we talked about great circles, we were circles enclosing the maximum possible area around the outside. Here, our lines, or at least our first type of line, are line segments that have maximum length going from one end of the disk to the other. And the second type of line is going to be a circular arc that is perpendicular to the outer circle, So what does that mean? That means take a circle and do something like this. Let me erase that. It is dotted. So, second type of line in our model basically says, take like a circle that intersects the unit disk and take only the parts of that circle that actually lie inside of our outer disk. And they have to do it in a way that makes it so that the two circles intersect at right angles. So, circular arc that ends up being perpendicular to the outer circle. So this would be one type of, one instance of a line in our model. Another one might look something like this. The dotted lines are just how the circle would continue outside of the disk, but we only care about the parts that lie inside the disk. Would this count? Good?
I think if you want a line that hits those two spots, you would want a smaller circle and put it a little farther in.
Alright, does this not work as is?
It looks like the 90-degree angles aren't there.
Yeah. We have to have the 90-degree angles in order to count. So here we have either very acute or very obtuse angle, depending on which of the angles you're looking at. So this one would not count in our model, unlike the first two ones. And so all of these, both the arcs and the diameters, are going to count as lines inside of our model. So unlike our other models where the lines kind of have a single definition, here, anything that's either one of these two types of things, the circular arcs or the diameters, are both going to be considered to be things we will call lines within the model. And then once we have our definition for points and lines, everything else is defined the way you would kind of expect. Between this on an arc or diameter, congruence is what you would expect, blah, blah, blah. And that is going to give us a new model on the unit disk. Any questions or comments? All right, I have a few questions for you that I want you all to start thinking about, given these definitions. First of all, which parallel property does this model have? Does it have elliptic, Euclidean, or hyperbolic parallel property to it? Second question, is this a Hilbert plane? Third question, what do triangle angle sums look like? Go. So go ahead and take a few minutes and see if you can answer any or all of these questions with your favorite classmates. Or if you're Megan. Oh, man.
Easy.
What's the rule for,
The small circle.
It's the IBC axioms, but like it's Monday.
yes, it is.
Oh, yeah, yeah.
Also, I'm feeling pretty small. Okay, yeah. Because I'm just thinking like if you have a certain point and you need to find 2 thirds, but you could adjust the size of the circle and like list it. Here's my question. Wait, I have a question actually.
Yeah.
Do the outside points down on the outer disk?
No.
Dang. Like the outer disk points. Like just.
This is a strict inequality. Does that eliminate some kind of example or counterexample? Well, it doesn't like you either.
So the first one I can do.
Is there
I was just gonna say,
Wait.
I feel like there isn't two, but Wait! But then
Okay, we established that in
Then what if it were like
Oh, we made it.
Wait a second.
Oh, you're right.
What's the definition of array in this?
The same as it is in every other model.
Like, can they be curvy?
Sure.
Okay.
Basically, array is a set of all points that are either on a segment, so snip off any line between 2 points and you get a segment. And also points like, if this is, so like if this is your A, then one of your, like, then one ray going through A could be like this set of points right here.
So look at that one, put the points, oh, the line segment, and the right corners, and then literally the way you screw off. So it's not a complete, so then I have to look at the rules for other things on. Well, we have to figure out what's going on. Oh, this is, but I need to figure out. For any number place, exactly one of the following must be correct. So, exactly, so we can mix them all up, it could be multiple. But we could be anything you want. It's not true any other directions. Let's just see. I can make one with less than that. I can make one out of less than. I feel like we can't, because what if you did this? And we took this, what if you did this? Or a greater than, you gotta draw greater than one, I'll draw less than one.
You've got
This is less than. I fell up for less than, you know, because this is curved, so these angles are gonna be less than. Yeah, exactly. So I don't know if we can do greater than, but we can try intersecting all these little parts. So it's like bowed out. You know, that's equal to? No, wait, greater than. I don't know if we can do equal to. I don't think you can, because you can't get 3 straight lines intersecting, like quarter triangle. Wait a second. Hold on.
You would
Didn't you do?
have
No.
to use the rounded part, but what is the
Okay, I'm gonna try and make a.
I don't know what constraints the right angle circle thing puts
How's
on.
it going along?
That's
We're working on number three now.
What do the triangle sums look like? It is one of those three conditions. You're either all equal to, all less than, or all greater than 100.
Oh, he said it's one of them. So we can't. Okay, so we did.
It does turn out to be one of these three.
Okay. Do not try to find an example for another.
There's not like a less than and a greater than.
Go back.
Because you can't reach your circle past it.
Maybe it's free.
You're not able to get 90 degree angles.
It's not, it doesn't have to be one of these, but it is one of these. I'll just, I'm not answering that.
Yeah, that's pretty cool. It's like the surface is so bad that they get so big that it's a straight line in the middle. And then they flip the other side.
Actually, parallel would be, parallel to the other circle would be very hard because it's either. Oh, I get, never mind, parallel. I'm thinking like inner. I don't know what I'm talking about. Have a nice day.
How is angle measured determined? If you have like two circle, or if you have like
Infinitesimal.
an arc of a circle, okay, so if you take like the tangent line to like the arc of a circle, like the two lines there, that would be like an angle measure.
Yeah, so basically if you like take something like this where you have a straight line intersecting with an arc. If you zoom in on that close enough, this looks like the same. If you zoom in close enough, it looks more and more like the angles we're used to that you can measure in the same way.
So if you have like a circle, you know, coming at a right angle, or sorry, the arc of a circle, which is a line, coming out of the same point that a diameter goes in, then that angle is 0 degrees.
So if we had something like that going in,
Yes.
yes.
0 degree triangle.
Although you can't include, although I don't think you could include a point like this because we're not including points on the outer circle itself. X squared plus y squared has to be strictly less than 1.
So then that doesn't count as a triangle because it doesn't intersect.
Because this is not a point in your model.
The edge is
No,
not
it's
aligned.
not a big deal.
So it would be a 0 degree angle, but I question whether that can actually occur in this model.
It's like, okay.
Is what I'm getting at. I think that gives us a reason why we specifically don't want to include points on the
I
circle.
was wondering why it was like a strict inequality. That's important.
Yes, that is important to avoid the sorts of 0 degree angles you're discussing. Good question. Good question. It sounds like everything's quieting down. So let's take a look-see at these. All right, what do y'all think about number 1? I'll tell you what, let's put it to a class vote. I'm going to read. 1 finger up for elliptic, 2 fingers up for Euclidean, 3 fingers up if you think it is the hyperbolic parallel property. 1, 2, 3, vote. You're looking like a gangster. Okay, let's see. Steph, why do you vote 3?
Because we just have a bunch of circles with the lines and they don't touch each other, so there's a bunch of parallel lines.
So let's say, I don't have an example on the board. So let's say if this is our circle, let's say, I don't know, this is our L. Here's our point P. You claim you can find multiple lines that pass through that P that are parallel to L? I found one. I found another. Neato mosquito, I agree. Yeah. This one is going to have the hyperbolic parallel property to them. Given any line L at any point P not on L, there always exist multiple lines passing through P that are parallel to L. Infinitely many, in fact. So this is a model that has the hyperbolic parallel property, similar to U, actually, where U was our model where points were the same, but lines were just straight lines that, any straight line that happened to intersect the circle, or the disk. This is a Hilbert plane. Megan,
No.
why not? Give me an axiom that breaks.
Oh, shoot, I think it's 3 for congruence axiom 3. It's the one that has to do with, 1? The 1, okay.
The 3 is the one that says if you take a line and say, basically, if this segment is congruent to this one and this one's congruent to that one, then the combination of these two is congruent to the combination of those two.
The one where, I think it's 1, where it's like, you have a ray and you have a line segment and you have, there's a point on that ray where you can construct a line segment that's congruent to that other line segment.
Ah, okay, so you're, okay, so yeah, I think that one's congruence axiom 1. So you're saying, in this model, you can find a line and a ray such that no point on that ray will make a segment congruent to the original line? Would you like to show us?
This is our ray, this is our line segment.
Can you draw your ray and like maybe make it a little more bold? It's hard, a little hard to see what you call it. Like that. And so you're saying there is no point on that ray that'll give you a segment congruent to something you provocatively called L?
Correct.
Any questions or comments for Megan about her drawing?
My question is, do you need points on L?
Points on
I mean, it'll be pretty easy.
These technically aren't points,
Or not?
but like, you have at least 2 points on L.
Oh, really?
Make your fighter. I mean, hold on. Before anybody gets angry.
I'm pissed.
I would expect that from you.
Oh, language.
What? Any question?
All right, thank you, Megan. So yeah, it turns out congruence axiom 1 fails. Call these points, I can barely see them. Let's call these A and B. I'm gonna call this one A prime. No point, I'm gonna call this R, on the ray R makes a line segment congruent to AB. So namely, congruence axiom 1 fails, which tells us, what's our conclusion from that, Megan?
And then it's not a Hilbert plane.
Not a Hilbert plane. Indeed. So unfortunately, we get yet another model that doesn't satisfy all the IBC axioms. And so finally, what do triangle angle sums look like in this model?
They would be less than 180 degrees.
All of them?
Yes, because as soon as you have one, you can't have it fluctuate between.
It's true. Either they all have to be less than 180, all equal to 180, or all greater than 180. In a Hilbert plane. Sorry. Sorry, I probably just have to repeat to the call on one of you, but I wanted to make a nice dramatic moment. We know that it's true in a Hilbert plane, but as Megan just explained, this ain't a Hilbert plane, so I don't think that proposition necessarily applies. That being said, you are correct that they are all less than 180 degrees. So this one. Doesn't have to be the same number, but they all are going to end up being less than 180 degrees. Even though it isn't a Hilbert plane, just so happens to satisfy that condition that comes out from being a Hilbert plane, that it is all less than 180 degrees. It's just that that's not guaranteed by the proposition that that's going to happen, if that makes sense. Any, yes?
What are the properties of the arcs in this case? Like how far to the midpoint of the circle could it go? Like could you have an arc that goes like across the diameter?
Something like this?
Yeah, could it like be further like that way? Could it have like 2 points incident to the diameter?
I don't know, you tell me.
That's what I was thinking, I don't really know.
If this is a Hilbert plane and we had all our instance axioms, we would certainly say that there can only be, two lines can only intersect at a single point at most. But this ain't a Hilbert plane. Could we have a single arc that intersects the diameter more than once? I think the
Like if
answer.
it went like you have the diameter and it goes like across. But I don't know what the angles would look like.
I think the problem is that would break the fact that the arc has to intersect the outer circle at right angles. Because, I mean, you could conceivably do something like this, if that's what you mean, but these aren't going to be right angles if you do that. It's a good question, but I think the answer is no, that can't happen. It's certainly something that shouldn't happen if this is a Hilbert plane, and I think even though this isn't a Hilbert plane, that can't happen. Steph, you're making, you just look like you swallowed something sour over there.
I just feel like that looks like you could make it.
Well, whose circle is
Does that look like a 90-degree angle?
The other ones look like 90 degrees.
The other ones are closer to being 90 degrees.
I just.
I was looking as I pretended for my trouble. Yes, Megan?
Isn't it kind of like the diameter is an arc in of itself, and it's creating that line? I mean, it kind of
Yeah,
so those are the 90 degrees.
Good. Way to predict my next question, which is going to be, why do we have two different definitions of lines? And the answer is, they're kind of the same if you think of the diameter as sort of being an arc of an infinitely large circle. So big that there's like practically zero curve, there's like zero curve to it. Because if you think about it, if we have little tiny circles, then obviously that looks pretty far from being a diameter, this segment here. If we were to have a really big circle, do something like that, this arc looks a lot more diameter-esque. And so the bigger and bigger circles we consider, the more and more these circular arcs appear to have less curve to them, at least the part that intersects the disk, and the closer they are to just being straight lines. That's a good question. I forget what you originally said. Question/observation. Yeah, technically, you could think of the diameters as being arcs of infinitely large circles that happen to intersect the disk perpendicularly. Yes, Stephen Becker?
I just tried to draw it.
How about that? So a preparatory disk is kind of a nice model. It gives us a model of hyperbolic geometry, like the original disk model U. Unlike U, if you recall, had 180-degree triangles. This has less than 180-degree triangles, which that serves as an illustration of how, Jack, this is something you asked me last week. Can we always say something about does less than, equal to, or greater than 180 degrees all correspond exactly to elliptic, Euclidean, hyperbolic? The answer is not necessarily. And then it's possible to have hyperbolic models, for instance, that are less than 180. It's also possible to have hyperbolic that's equal to or even greater than 180. It's just that if you have Euclidean implies it has to be in this category of exactly 180 degrees. There is sort of a loose association in that if you see less than 180, it's probably hyperbolic. If you see greater than 180, it's probably elliptic. If you see equal to 180, it's likely, but not necessarily Euclidean. But that's not a hard, fast rule. All right, new packet time. So now that you've all mastered triangles, we're ready to go up a segment and talk about quadrilaterals instead. Yeah, pass that. So Jim didn't have to get up.
So we'll be at heptagons.
Thank you.
Good enough. So just like with the last couple packets, assume for all propositions and such that we're going to be working over a Hilbert plane, unless we explicitly say otherwise, or are looking at a specific example of something that we know is not a Hilbert plane, like spherical geometry, U, or the Poincare disk. And quadrilaterals. So in this packet, we're going to be looking at properties like, just like how in R2, in Euclidean R2, all triangles have to have 180 degrees. In R2, a quadrilateral usually has 360 degrees. Is that going to be true in an arbitrary model? Probably guess the answer to that is negative. You would be correct to assume no. We're going to be looking at some of those relationships as well as how do angles, parallel this, etc., work in quadrilaterals. And specifically, we're going to be looking at two classes of quadrilaterals in this packet. Sakari quadrilaterals, which we'll talk about today, and then Lambert quadrilaterals, which we'll get to probably on Monday, or next class. So to start, we're going to say that a Sakari quadrilateral ABCD is going to be one where our base angles, angle A and angle B, are right angles. And the two sides, specifically only the sides, not like all four sides, but AC is congruent to BD. So if we draw out what a Sakari quadrilateral is going to look like, it's going to look something like this. Where if this is A, this is B, this is C, this is D. We want the two angles at the bottom to be right angles. And we want the two things on either side, we're going to call these the sides, to be congruent. The bottom we're going to call the base, the top we're going to call the summit, because Sakari was a mountain climber and loved to name things based on, no, that's, actually I don't know if that's true. But this is just kind of the names that we refer to typically, the different sides of a Sakari quadrilateral. Bottom one's the base, top is the summit, sides are sides. Where have we seen the name Sakari before? Okay.
He did the one about how in Hilbert planes triangle angles are adding up to 180 or less or more, right?
Yeah, that was, if you recall, that was the Sakari angle theorem, which said that if, which is a theorem that said in a Hilbert plane, all the triangles have to have some angle sum, have to have triangle sums, let's use our notation, less than 180, all equal to or all greater than 180 degrees. Also, he got partial credit for the Sakari-Legendre theorem, which is the one that says they all have to be less than or equal to if Archimedes' axiom holds. So this is a specific type of quadrilateral where our two angles at the bottom are right angles, and on this, and our two sides we're assuming are congruent to each other. So let's say we're working with R2. if these are going to be congruent to each other, and these are going to be right angles, what else would have to be true in R2? No looking at the theorem on the bottom of the page. See?
Angles C and angle D are also right angles.
It's going to turn out to be the case that if we're working in R2, this is enough to tell us that these would also have to be right angles. And what else? That?
The summit and the base are the same length.
Yeah, the summit and the base would have to be congruent. These are like the usual tick marks that you say, hey, 2 tick marks say these are congruent. I'm dotting them in because this is R2 specific. And so, Trudy, if we have a quadrilateral with 4 right angles, and the summit and base are congruent, and the 2 sides are congruent, what kind of quadrilateral is this going to be in R2?
A rectangle?
Indeed. They call it an angle that's been an accident, a rectangle. So it's going to turn out to be the case that in R2, Sakari implies a rectangle. As we'll see though, if we're not working in R2, that doesn't necessarily have to happen. So we will prove though that in R2, if you have something that's Sakari, meaning the bottom 2 angles are right angles and the 2 sides are congruent, then the whole thing has to turn out to be a right angle. So, and we've got time for this. Let's start off by proving the part where we show that in a Hilbert plane, the summit angles have to be congruent to each other. So I'm not writing out in a Hilbert plane, but like it says at the top of this page, for all theorems and propositions, unless I say otherwise, assume we're working in a Hilbert plane. So the summit angles of a Sakari quadrilateral must be congruent. So it turns out that at any Hilbert plane, the 2 sides here are congruent and these 2 angles are right angles. Angle C and angle D up here are going to have to be congruent to each other. Notice that I didn't say they have to both be right angles, but they are going to have to both be congruent. Let's see if we can prove this. So to start with, I'm going to notice a couple of things. I'm going to say that since AC is congruent to BD, that's by assumption, AB is congruent to itself. The base is congruent to itself. Dr. Ursula, isn't that obvious? Just wait a second. And angle A is congruent to angle B. Something has to happen. So we're assuming AC is congruent to BD. We're assuming this side is congruent to this side. And we're assuming that the angles in between these congruent pairs of sides are equal to each other. What property does it feel like we're about to use? Yeah?
Parallelism.
Ooh, what kind of parallelism?
We can say that AB is a transversal that cuts AC and BD, and so then AC and BD are parallel.
We could certainly say that.
Right angles.
Yeah, we could certainly say something like that, that since they're both perpendicular to the same thing, AC and BD have to be parallel to each other. That's not what I'm going to go for here, though, because all that really requires is that these 2 angles are right angles, these 2 are parallel. That wouldn't rely on AB being congruent to itself at all. So we have 2 pairs of congruent, we have this side is congruent to that side, this side is congruent to itself, and the angles in between these two congruent pair of sides are congruent, right?
I mean, if you want to draw triangles, you can use sine angle sine.
Yeah, this actually, I would say that these three things smell to me like a side angle side argument is coming along.
You still know.
Specifically, if we draw up these segments here, we can say by side angle side, the triangle CAB is going to be congruent to triangle DBA. And what I specifically want from that is that I want that BC is congruent to AB. That the two diagonals of this rectangle are congruent. So basically, here we're using that the bottom left triangle here from C to A to B is congruent to the bottom right triangle DAB, or DDA. I'm going to call it DAB. Or no, it has to be DDA. And so, because the two sides of these two triangles are congruent, the bottom of the bottom left triangle is congruent to the bottom of the bottom right triangle, and the two angles, and these are both right triangles. The angles in between the congruent sides are congruent, so side angle side applies here. And we know we have side angle side because we're working over a Hilbert plane where congruence axiom 6 is side angle side. So now we know the two diagonals are congruent. So now I'm going to say, then since CD is congruent to itself, BC is congruent to AD, and AC is congruent to BD. So now I'm saying this side is congruent to itself. Our two diagonals are congruent, and we still have that this side is congruent to this side. So in other words, the sides of the top left triangle, all three sides, are congruent to the three sides of this top right triangle. What does that tell us about these two triangles if all three of their pairs of sides are congruent to each other? Jack?
The two triangles are congruent.
By?
Side, side, side.
Indeed. Now we're going to once again apply a triangle congruence property, except this time it's not congruence axiom 6, side angle side. We're going to be applying the proposition that is side, side, side. And so if we were to apply side, 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 Jack, which two triangles can we then say are congruent to each other?
Triangle CAD and triangle DBC.
Triangle CAD and triangle DBC?
Yes.
Indeed. So the top left triangle now has to be congruent to the top right triangle. And then that's just going to tell us that since the top left and top right triangles are congruent, these two angles then have to be congruent to each other. Thus, since triangle CAD is congruent to triangle DBC, we can say that angle ACD, I will say angle C is, no, triangle, or angle ACD is congruent to angle BDC. And there we go, there's our proof. By side angle side, the bottom left and bottom right triangles are congruent. So the diagonals are congruent of this quadrilateral. And then by side, 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 the top left and top right triangles are going to have to be congruent to each other. And that means that these two angles then have to be congruent. Jared, you look like you have something you want to say.
No, I didn't.
Okay, you had your I have something to say face on.
Ooh.
Any questions or comments about this proof? So now that we've proven these two angles, angle C and angle D are congruent to each other, I think we should try and prove next that they're both right angles. Megan, you said, you whispered no, why not?
I don't know, it feels like something that would hold in like spherical geometry. So,
Well, spherical geometry is not a Hilbert plane, so who cares about spherical geometry?
yeah, it just doesn't seem like it's gonna hold.
You are correct not to fall for my trap. Turns out, while these two top angles, the summit angles, are in fact going to always be congruent to each other in a Hilbert plane, that doesn't mean they're both going to be right angles. He knows my stratagems all too well. So let's take a look at some Sakari quadrilaterals in a couple different models. So if we draw one out on the sphere here, let's see. I'm going to draw something that'll look like a Sakari quadrilateral in spherical geometry. Let's use everybody's favorite. Draw line segments from the North Pole to the equator. And I do that because I know that's always going to give me right angles. Having multiple right angle triangles in the spherical geometry is a nice property to disprove things. And let's do another one. Great circle from here to something like that. So our Sakari quadrilateral that we're going to be looking at here is going to look like this. So these two sides I drew to be congruent. The quadrilateral, our two base angles are right angles. What can we say about our summit angles here? Lacey, what does it look like is going to be true about these two summit angles?
They both don't look like right angles, they look like they're greater than right angles.
Yeah, those are both obtuse angles. So while this angle is going to in fact be congruent, again, not by our theorem, because spherical geometry is technically not a Hilbert plane. We can say, though, that the two summit angles of our Sakari quadrilateral are both obtuse. They're still congruent to each other, but they're not right angles like they would be in Euclidean geometry. They're going to be obtuse. And then, let's do point radius really quick, because this won't take long. So if I draw out in, let's label this S2. Point radius. Let's see. We're going to have one go like here. We're going to have one go like here, here. So we get and they'll have one go like this. These two sides are congruent. So we can get a Sakari quadrilateral in the Poincare disk that looks like this. Emma, what does it look like the two summit angles in the Poincare disk Sakari quadrilateral look like?
Very cute.
They're cute! Aren't they a cute little thing? So the moral of the story is, in a Sakari quadrilateral, pretty much in any of the models that we're looking at, you're always going to get that the summit angles are congruent to each other. But in Euclidean geometry, they'll be right angles. In other models of geometry, they're not necessarily going to always be right angles, due to how lines can bend and stuff in non-Euclidean models. All right, that'll do it for today. When we come back, we are going to discuss The other type of quadrilateral in this packet, which is the Lambert quadrilateral. Y'all have a good rest of your day. I will see you all on Wednesday.